Polarization. What is polarization? When a wave is passing through a medium, if the vibration of the particles is confined to a single plane, such a phenomenon is called polarization. When a wave is passing, if the vibrations of the particles is confined to a single plane, such a phenomenon is called polarization. The wave is called polarized wave. We know that light wave is composed of oscillating electric and magnetic fields. Light wave is composed of oscillating electric field and oscillating magnetic field. The electric field vector is normally used to study polarization. To study polarization, we use electric field vector. Since the effect of magnetic field vector is negligible, on human eye or light detectors. On light detectors or on human eye, the effect of electric field vector is maximum and that of magnetic field vector is negligible. A light beam in which the electric field vectors vibrate in all planes, in all possible directions, is called unpolarized light. In a light beam in which the electric field vectors vibrate in all possible planes is called unpolarized light. This is the case of light emitted from a source. When the light is emitted from a source, the electric field vectors of a beam will vibrate in all possible directions. It is represented by arrows in different directions. Here the arrows in different directions shows unpolarized light. Here we have to imagine that the light ray is coming out of the screen. When we see the incoming light beam, we notice the electric field vectors to be situated in different planes. A light beam is composed of unpolarized light. A light beam composed of unpolarized light is imagined to be composed of two perpendicular components. These different electric field vectors in different planes, they will be resolved into two perpendicular directions, and this will be imagined to be composed of only two perpendicular components. A light beam which is composed of unpolarized light is imagined to be composed of two perpendicular components. Though there will be different directions, we imagine those are resolved into two perpendicular components. In the figure, the double arrows represent the components in the plane of the screen. The horizontal line indicates the direction in which the beam is passing. The horizontal line indicates the direction in which the light beam is passing. Double arrows represent the components in the plane of the screen. Dots are perpendicular to the plane of the screen. Dots will be in and out of the screen, perpendicular to the plane of the screen, whereas the double arrows are situated in the plane of the screen. A polarized light beam consists of only one component. We have seen two components, double arrowed component and dot component. But actually, if a beam consists of only one component, then it is called as a polarized beam. One type of polarized beam can be represented by double arrows. The components in the plane of the screen constitute one polarized beam. The components perpendicular to the plane of the screen, represented by dots, it is another polarized beam. Polarized dot components, polarized light with arrow components. So we can imagine to be two polarized components. Polarized light can be produced by any of the following methods. We can separate these components. For separation of these components, we require certain processes, certain methods. The methods that are used in producing polarized light are reflection, refraction, and double refraction. The methods of producing polarized light. The method of producing polarized light is reflection, refraction, and double refraction. These are the methods using which we produce polarized beams. Now let us study them in detail. Polarization by reflection. Polarization by reflection. Let us consider PQ as the separation of two media. In the downward direction, it is denser medium. In the upward direction, it is rarer medium. And a ray is incident along the path AB. Unpolarized light beam is incident along the path AB. And a part of it is reflected along BC. A part of it is reflected along BC. Another part is refracted. That refracted part is BD. BD is the refracted part which goes to the second medium, and BC is the reflected part. As the angle of incidence changes, for a particular angle of incidence, the reflected beam consists of only the dot components. The reflected beam consists of only dot components. That is, it is polarized beam. The reflected beam is completely polarized for a particular angle of incidence, but not the refracted beam. The refracted beam is not polarized. It consists of both the components, but the reflected beam consists of only the dot components. So it is completely polarized for a particular angle of incidence. In the case of reflection, the beam will be polarized if the angle of reflection is the angle of incidence. If the angle of incidence is 57.5 degrees in case of a glass reflecting surface. If glass is the reflecting surface, then the angle of incidence for which the reflected beam is completely polarized is 57.5 degrees. Now we use this condition for producing polarization by refraction. Polarization by refraction. For producing polarization by refraction, we take a cylindrical metallic tube. A cylindrical metallic tube will be taken, which has some opening at the top. Along the axis of this tube, glass plates are placed. Glass plates are placed at an angle of incidence, at some incline, at an angle of inclination 32.5 degrees. The glass plates will be placed along at an angle 32.5 degrees with the axis of this tube, and they will be placed near the opening of this glass tube, of this metallic tube. When a beam is unpolarized beam, light beam is incident along the axis of this tube, when an unpolarized light beam is incident along the axis of this tube, then it will be incident on each glass plate at an angle 57.5 degrees. An unpolarized beam which is incident, which passes along the axis of this tube, will be incident on each plate at an angle 57.5 degrees. Then the reflected beam will be completely polarized. The reflected beam is completely polarized, and the refracted beam it consists of both components, double arrowed component and dot component. The dot component is very small, whereas the double arrowed component is very, very large, because dot component is reflected from this, dot component is reflected, hence the refracted beam consists of, no doubt, double arrowed component and dot component, but the dot component is very small. And this beam, it undergoes reflection and refraction at the second plate. The beam that passes through the first plate will be incident on the second plate once again at 57.5 degrees, and once again both reflection and refraction takes place. In the reflected beam, once again we notice some more dot components. So some of the dot components are removed from this component, refracted component from the first plate, and the refracted beam in the second plate, it will have a small number of dot components, and this undergoes successively refraction through several plates. If we keep some 15 to 20 plates, the entire dot components will be reflected. The entire dot components will be reflected by the time the beam passes through some 15 to 20 plates. So the emergent beam, the refracted beam, is now completely polarized, and it consists of only double arrowed components. This refracted beam is polarized. So this is how we produce polarization by refraction. Double refraction or birefringence. Double refraction or birefringence. Let us take a crystal, either made of quartz or calcite. Crystals will be cut such that their properties are symmetrical about a plane. About a plane, the properties of this crystal, the substance, are symmetrical. Such a plane is termed as optic axis. Optic axis. When we observe an object like an ink dot through this crystal, we notice two images of that ink dot. One image is formed due to the rays which are refracted as ordinary refraction, known as ordinary refracted beam ray, and another image is produced by another type of refraction known as extraordinary beam. One dot is produced by ordinary refracted beam, another image is produced by extraordinary beam. Extraordinary beam. When we rotate this crystal, one dot remains constant. That dot is known as the ordinary beam dot. Another dot rotates about this dot. Another image rotates about the first image. Such an image is produced by extraordinary beam. So we notice two images by a crystal. One is produced by ordinary beam, another is produced by extraordinary beam. These two beams can be identified by rotating the crystal, placing on an ink dot. One ink dot will remain stationary, another ink dot will rotate about this. The rotating ink dot is produced due to extraordinary beam, and the stationary dot is produced by ordinary beam. Both these light beams are polarized. Both these light beams are polarized. One light beam is produced, it is polarized in the plane of the crystal axis. Both the rays travel along the same direction if incident ray travels along the optic axis. So these two dots, they coincide if the rays are traveling along the optic axis. The ordinary ray is polarized along the optic axis. The ordinary ray is polarized in the plane of the optic axis. The extraordinary ray is polarized perpendicular to the optic axis. Both will be polarized. Ordinary ray is polarized in the plane of optic axis. Extraordinary ray is polarized perpendicular to the optic axis. The secondary wavelets in ordinary ray are spherical in nature. The secondary wavelets in ordinary ray are spherical, whereas the secondary wavelets of extraordinary ray are ellipsoidal. Double refraction in calcite crystal. Double refraction in calcite crystal. Generally, crystals will be cut about a plane, according to a plane known as optic axis. Its properties will be studied about this plane, and they will be easy to study and symmetric. Such a plane is known as optic axis. Now here the optic axis is shown intersecting the angle 109 degrees. Now let us suppose a ray is incident from the left on one surface of the crystal. Its angle of incidence is I. Then the ray undergoes refraction. It is not incident along optic axis. So it undergoes double refraction. So there will be two refracted rays inside the crystal. One ray corresponds to ordinary ray. The other one is extraordinary ray. The angle made by the refracted ray with the normal is known as angle of refraction. So RO is the angle of refraction for ordinary ray, and RE is the angle of refraction of the extraordinary ray. RO is the angle of refraction for ordinary ray. This angle is constant for a given angle of incidence. RO is constant for a given angle of incidence, but RE varies with the angle of incidence. RE is not constant for angle of incidence. The refractive index for ordinary ray is given by mu O is equal to sin I by sin R0. The refractive index for ordinary ray is given by mu O is equal to sin I by sin R0. The refractive index for extraordinary ray is mu E is equal to sin I by sin RE. Sin I by sin RE is refractive index of extraordinary ray. The refractive index for ordinary ray is a constant, but not for extraordinary ray. So mu O is constant, but not mu E. Mu E changes with angle of incidence. Mu E changes with angle of incidence. Propagation of O ray and E ray inside the calcite crystal. Propagation of ordinary ray and extraordinary ray in the calcite crystal. When a light ray enters isotropic medium like glass, it undergoes refraction and the refracted ray travels with constant speed in that medium. The secondary wavelets of this ray are spherical. In an isotropic medium, the ray travels with constant speed and the secondary wavelets are spherical. In a crystal, if a ray enters along the optic axis, it travels undeviated, and both the rays, ordinary ray and extraordinary ray, travel along the same direction and with the same speed. The speed and direction of O ray and E ray will be the direction of optic axis if the ray is incident along this direction. If the ray enters perpendicular to the optic axis, the difference in the speeds of the two rays is maximum. The difference in the speeds of the two rays, O ray and E ray, is maximum when they enter the crystal perpendicular to the optic axis. In any other direction, the speeds are different. The speeds are different in any direction other than the direction of the optic axis. The speed of extraordinary ray varies with angle of incidence I. The speed of extraordinary ray varies with angle of incidence I, whereas the speed of ordinary ray is constant. The speed of O ray is constant, but that of E ray, it varies with angle of incidence. Ordinary ray obeys Snell's law, but not extraordinary ray. E ray does not obey Snell's law, but O ray obeys Snell's law. Snell's law is obeyed by ordinary ray, but not by extraordinary ray. Polarized. In some crystals, after double refraction, one of the rays is absorbed strongly, and the phenomenon is known as dichroism. When double refraction takes place in a substance, in a crystalline substance, one of the rays, ordinary or extraordinary, is strongly absorbed. Such a phenomenon is known as dichroism. So only one polarized light will come out of that crystal. One is absorbed, the other one is transmitted. So only polarized light will come out of the crystal when an unpolarized light is passed through a polarized. If an unpolarized light ray strikes a tourmaline crystal, if an unpolarized light ray strikes a tourmaline crystal perpendicular to its axis, optic axis, double refraction takes place and the ordinary ray is completely absorbed. So tourmaline crystal gives polarized light, which is consisted of extraordinary rays. Such a crystal can be called as polarized. But in practice, a polarized is a thin transparent film containing tiny synthetic crystals with their optic axis parallel to one another. Generally, we call a polarized as a thin transparent film in which tiny crystals, which have the property of dichroism, they are placed with their axis parallel to one another, with their optic axis parallel to one another. Such a thin film of transparent material is called as a polarized. A polarized produces polarized light. In modern times, long chains of polyvinyl alcohol molecules oriented in a preferred direction and stained with ink containing iodine are used as polarides. In modern times, long chains of polyvinyl alcohol molecules oriented in a preferred direction and stained with ink containing iodine are used. Polaroid sheets are used as polarizers. And analyzation of polarized light. Analyzation of polarized light. Let us take a source of monochromatic radiation, source of monochromatic light. Before that source, place two crystals. We have chosen two crystals P and A. In fact, both of them are polarides. P is one polaroid, A is another polaroid. Keeping P in front of the source, observe the light coming from P and rotate the crystal P. If the crystal is rotated, whatever may be the orientation of its optic axis, we notice light coming out of P. Light will come out of P whatever may be the direction in which the optic axis of P is situated. But if we keep another crystal A such that its optic axis is parallel to the optic axis of P, then we notice light emerging from the crystal A. Light will emerge out of the crystal A if its optic axis is parallel to that of P. Now, keeping the crystal P constant, rotate the crystal A. As the crystal A is rotated, we notice the intensity of light to be decreasing. The intensity of light decreases as A is rotated, and the intensity becomes 0. That means no light will come out of the crystal A when its optic axis is perpendicular to that of P. When the optic axis of A is making an angle 90 degrees with the optic axis of P, then there will be no light emerging from the crystal A. From this, we notice that the light coming out of the crystal P is polarized light. This phenomenon can be explained using an analogy of slit and rope, which we are going to analyze. Now, the light between the source and the crystal P is unpolarized, as shown below. And the light between the Polaroid and the analyzer is polarized light, which consists of only double arrows. Slit rope experiment. Physical analogy to the action of the crystal can be drawn from the mechanical waves on a rope passing through a slit. We can draw physical analogy to the action of light waves from the waves on a rope which passes through a slit. For example, a rope is passed through a slit and pulses are created on it. When longitudinal pulses are created in the rope, the longitudinal pulses will pass through the slit. Whatever may be the longitudinal pulse created, it will pass through the slit. But if a transverse pulse is created, parallel to the length of the slit, it will pass through the slit. Whereas a transverse pulse created perpendicular to the width of the slit, it will be stopped. The transverse pulse, it passes through the slit if the vibration, plane of vibration is parallel to the slit. If the plane of vibration is perpendicular to the length of the slit, then the pulses will be stopped. So transverse vibrations can only be stopped, but not longitudinal vibrations. This analogy can be applied to light waves. We have seen that light waves come out of the analyzer when its optic axis is parallel to the polarizer. That means the plane of vibration of the light rays, the plane of vibration of the electric field is parallel to the optic axis. That is why the vibrations have passed through, the electric field vectors have passed through the analyzer, the second crystal. When the crystal is rotated by 90 degrees, the plane of vibration of electric field vectors is perpendicular to the optic axis. Hence, the rays are cut off. So we don't see any radiation coming out of the slit when the crystal is rotated by 90 degrees. So the plane of vibration, if it is parallel to the optic axis, the rays will pass through the crystal. If the plane of vibration is perpendicular to the axis of the crystal, then the vibrations cannot pass through the crystal. Plane of vibration and plane of polarization. Plane of vibration and plane of polarization. Consider the polarized light as shown in the figure. Here, this polarized light consists of double arrowed lines which are situated in the plane of the screen. Notice the plane represented by white background, white line, solid line is the plane of vibration. It lies in the plane of the screen. The electric field vectors of the polarized beam are in the plane of the screen. So, plane of the screen is called the plane of vibration, or the plane in which the vibrations of the electric field vectors are situated is known as plane of vibration. The plane perpendicular to the plane of vibration and that contains the direction of propagation is called the plane of polarization. We have to imagine here the plane of polarization to be perpendicular to the screen. It is perpendicular to the screen and passes through the arrow which represents the direction of propagation of the polarized light. The plane represented by the dotted lines should be imagined to be perpendicular to the screen and along the direction of propagation. That is the plane of polarization. Electric field vectors will be perpendicular to the plane of polarization. If we consider the polarized light to be composed of the dot components, then the plane of polarization is the plane of the screen, because these components, they are perpendicular to the plane of the screen. Hence the plane of the screen becomes the plane of polarization, and the plane perpendicular to the screen, which is represented by the dotted background, dotted line, that is the plane of vibration. So here the plane of vibration is perpendicular to the screen and plane of polarization is the plane of the screen.